I have had the pleasure of speaking to ICCF conferences before. I think I'm known as the crazy guy with a crystalline New Age model of the nucleus, lots of colors and geometry, that I would like to talk about a little bit later, mostly tomorrow evening. But before that, I want to start with something I think is more important for nuclear theory in general and LENR as well. The right button. The left button. Thank you. I'd like to start with my conclusion and summarize with what may seem a little bit irrelevant, but is in mainstream nuclear physics is, I think, quite important, and that is developments over the last decade or so by a guy named Meitner in Germany, who's worked on something called nuclear lattice effective field theory. Oh, sorry. Now, what's interesting about his work is that he is drawing conclusions about nuclear structure at a level of spatial detail that is forbidden by the uncertainty principle. And this is something that he does quite successfully and quite frequently in publications. Now, it's interesting because it does contradict the dominant Copenhagen tradition in quantum mechanics, which was originated by Bohr and supported by Heisenberg and Pauli, and fought against by Einstein and others, and is essentially an unresolved issue. But nonetheless, there has been a dominant view, which is called the Copenhagen interpretation. Now, you're probably all familiar with the uncertainty principle. If you localize a particle in space, that localization itself cannot be measured simultaneously with equal precision of, for example, the particle's momentum. There's a trade-off there. Now, I think the uncertainty principle itself is widely accepted by Einstein and others, but the interpretation is quite different considering what the particle's actual properties are relative to what our understanding of our knowledge of the particles are. So, going back a few decades, looking at lattice possibilities for nuclear structure, I wrote up a paper in the 70s, sent it off to a journal, and the referee's comments were, well, this is inconsistent with quantum mechanics. It's a non-starter. A liquid nucleus, a gaseous nucleus, a cluster nucleus is fine, but a lattice demands localization of the particles and therefore cannot exist. Now, you're probably familiar with this. This is goes back to the Solvay conferences in the 1920s, and every few years books are printed again and again, arguing for or against the Copenhagen view, again without resolution. But what I think is quite interesting is that Bohr's own views, developed in the 1920s, he came to his views before the discovery of the nucleus, before the discovery of the neutron, before any ideas of nuclear structure at all. Nonetheless, he was quite a powerful personality, and as a consequence, all of nuclear theory has been developed within the framework of Bohr's ideas. This is very rarely commented on. I found this in Byrne's book from a few years ago, where he says that the Copenhagen philosophy has completely dominated nuclear theory throughout much of this century. And I think that's quite interesting because you don't hear much about the Copenhagen view or the interpretation of the uncertainty principle within the framework of nuclear physics. You hear it a lot with regard to electron physics, but not nuclear physics. Now I just want to show you what it is that Meister's been doing, which is quite contrary to this. So he starts off with a lattice of some kind and places protons and neutrons in the lattice and then does quite sophisticated supercomputer calculations about the interactions of the particles and then draws conclusions about the structure of any given nucleus. So here's a two-dimensional lattice with up to 4 particles, spin and isospin combinations, on the same lattice position. And of course, he does that in a 3-dimensional lattice, sometimes neutrons only, sometimes protons and neutrons. But the whole thing, it's a random network with fancy nuclear force calculations to calculate the binding energy of any given configuration. So most of his work has been focused on things like alpha clusters and oxygen. So here's 16 protons and neutrons located on 4 lattice sites. And he calls this almost a regular tetrahedron. It's sort of a tetrahedral structure. And an alpha cluster, again, 3 lattice positions. The lattice points are separated by about 2 Fermi. And if that is the case, then each of these nucleons should have too much momentum to be a part of a stable nucleus. So this is what Meister has been doing. And inconsistent with the dominant Copenhagen view of quantum mechanics. You probably know that there's something also called the lattice theory at the QCD level, and this is very similar. They use a more fine-grained lattice with the localization of quarks within that. The difference is that in lattice quantum chromodynamics, nobody is drawing conclusions about the location of the quarks within the nucleus, within a nucleon. Whereas what Meister has been doing is drawing conclusions about the actual structure of the location of the protons and neutrons in a nucleus. So these are, in a sense, very different techniques. Again, Monte Carlo randomization, fancy supercomputer calculations, but not drawing conclusions about the location of quarks versus drawing conclusions about the location of protons and neutrons. Now, for most of you say, well, so what? This is some kind of theoretical development in nuclear physics. But what is interesting is that Meister's work has drawn the attention of the European Physical Society, who recently, 2 years ago, gave him the Lisa Meitner Award in Nuclear Physics, which is maybe one step down from the Nobel Prize, but it's quite an honor, the only international prize in nuclear physics for specifically this work that is inconsistent with the Copenhagen interpretation. That, in a sense, is what I wanted to say, that there is, from the point of view of the European Physical Society, doing work which is numerically sensible is fine, even in violation of the Copenhagen interpretation, if you're doing sensible numerical calculations. So what this means is that despite the fact that every now and again there have been lattice models published in the literature, they are considered unconventional. I have myself battled with referees and editors. Maybe you know John Maddox, 22 years editor of Nature, a strong Copenhagen fan. Philip Abelson, editor of Science, strong Copenhagen fan. Leon Rosenfeld, an acolyte of Bohr himself, 20-something years, editor of Nuclear Physics. These guys have been keeping the Copenhagen interpretations front and center in nuclear physics and keeping out unconventional ideas. Now, the point that I want to make here is certainly in violation of Bohr's interpretation of the uncertainty principle, but the uncertainty principle itself is not being violated. This is not a violation of quantum physics. It's a violation of Bohr's philosophy concerning that. So for this reason, I'm using this word renaissance in nuclear physics. If it is possible to say that now non-Copenhagen views of the nucleus are acceptable as a theoretical approach. Meitner himself is very gung-ho, of course, and has talked quite a bit about the ab initio nuclear theory, predicting nuclear properties from basic principles using his technique. Now, the analogy that I'd like to draw here is that what Meitner has successfully done, I think, is what Kekulé did in the 1850s, and that is talk about structure where nobody wanted to talk about structure. In the 1850s, it was not a quantum mechanical issue. It was just nobody wanted to believe that there was all kinds of substructure issues that need to be dealt with. In the post-quantum era, I think there's a similar reluctance to deal with more fine structure than needed, and this time now with the rationalization of the uncertainty principle. So what Kekulé did, as you probably know, he had C6H6 as the formula for benzene, and he called that a hexagon, and he was ridiculed, of course, couldn't publish for years, and then eventually this came about as standard molecular structure stereochemistry and is well accepted today. Of course, there's still arguments about structure, even for something like benzene, but the idea that there is structure behind the C6H6 formula is no longer controversial. So what I think Meitner has done is to play the role that Kekulé played in chemistry in opening up the doors to more detail in nuclear structure than most nuclear theorists want to think about. So beyond that, there's the question, okay, what kind of structure should we be concerned with? And here there are lots of different ideas, most of them unpublished in the mainstream media, a lot on the internet, but those that have been published in the physics journals include Meissner's simple cubic packing lattice, which I think is myself wrong for various reasons, but I nonetheless think that Meitner himself should be considered a hero for nuclear theory insofar as he's opened up the path to discussion of substructure. The other alternative lattice is what I call Wigner's FCC lattice, and this was published by Wigner in 1937. I have a picture of that later, and this is the lattice that I've been interested in for some decades now. There'll be some discussion of the details of that lattice on tomorrow evening. The main point that I want to make is simply that there's a lot of possibilities for discussing transmutation issues if we can get beyond the amorphous liquid drop model, the amorphous gas phase of the shell model, and get to substructure. Beyond that, then there's simply the issue of how to deal with lattice structure with nucleons planted in positions, and that is all solid geometry, and it's simply numerical, easily done if computation is sometimes complex. So my suggestion or plea is to theorists to interact with those of us who are interested in substructure. That is to say, we need mechanisms, quantum mechanical mechanisms, particle mechanisms that we can plug into structures, and specifically the lattice structures that have been published. So these are the real theorists in cold fusion research, Muhlenberg, Hegelstein, and others who are doing interesting things, but generally not dealing with large, realistic nuclei, the many-body problem of the nucleus. So the framework here that I just would like to mention is that there are different levels of quantum mechanics, the QED, which is essentially chemistry, QCD, which is very high energy and probably irrelevant to what we're doing here, and something in between, QND, which Feynman and others in the 1950s talked about, which is nuclear reactions at the level of a few MeV. And I think this is where the future of cold fusion theory must be. Finally, the point I want to make about Wigner's lattice is that it is isomorphic with the shell model, which is to say it has the same symmetries as the independent particle model and is, in that sense, is well known. It is the independent particle model itself began with Wigner's work in 1937, ended up with a Nobel Prize for that work in 1963, but the geometry that he talked about and published in Physical Review has been completely ignored. All of the energy levels, of course, are central to the independent particle model, but the structure that underlies that has been forgotten or neglected. So QND is a phrase that came up briefly, but I would say that the structure behind QND is in fact known. It's known as the independent particle model, but the structure itself is a face-centered cubic lattice with symmetries which reproduce the independent particle model symmetries. The details of that are the geometry that I've been at for a few years. This stuff is all published. The book that I wrote a few years ago is no longer for sale from Springer for some reason, but it's available on Amazon for $700 if you're interested, or you can download it from my homepage, whichever you prefer. But the point is that Wigner's lattice and Meissner's very successful, politically successful simple cubic lattice are completely unrelated. It's the symmetries of the FCC lattice that are reproduced, that do reproduce the symmetries of the independent particle model, whereas the simple cubic lattice has none of those symmetries. So it's really Wigner's work that I think we've got to go back to. I don't know what it is, but in the 1930s, so many wonderful things happened, and then were soon forgotten, and things drifted off in the direction of quarks and string theory and other incomprehensibles, whereas some of the really sensible stuff that was published in the 30s has sort of remained undeveloped. So this is what I will hope to discuss with people interested in plugging mechanisms into a lattice tomorrow evening. Wigner's paper itself, Symmetry of the Nuclear Hamiltonian, is from 1937, and there he states quite clearly the quantum numbers are all half integers whose combinations form a face-centered cubic lattice, a sentence that has never been quoted anywhere by anyone, I believe, and followed by Nobel Prize, and in fact the Nobel Prize citation includes the citation of a paper from 1937 and the discovery of fundamental symmetry principles. Got a few minutes. I just want to mention what symmetries of the nuclear Hamiltonian means. That doesn't mean much to most people who speak English, but it's the Hamiltonian idea is familiar to most of us in terms of electron structure, where you have quantum numbers, n, l, m, whatever, which are related to specific geometry of electrons, and this is what chemists are interested in. But it's the quantum numbers that are at the heart of this thing that give these symmetries and the relationship among the different quantum numbers. So you get tables like this in all of the chemistry books from the 1930s. So any given electron will have a specific set of quantum numbers uniquely, and therefore a unique geometry within the atom. This is the atomic Hamiltonian, and this leads directly to the periodic table, the prediction of inert gases and things like that, and all the occupancy and energies of the different electron states. The point is that call it the independent particle model, call it the shell model, call it the FCC lattice, call it Wigner's model, whatever, there's exactly the same kind of table, tabulation of possible nucleon eigenstates, their occupancy and relative filling, and prediction of essentially closed shells, which are the magic numbers. And this is usually expressed as the harmonic oscillator in the textbooks, where again it's the quantum numbers play a key role, and the relationship among the quantum numbers gives you the entire symmetries of the nucleus. Top center there is Wigner's hand-drawn picture from 1937. This was rediscovered by several people in the 50s and the 70s, and I came along, did the same thing, stood at the only photocopying machine at Princeton in front of Eugene Wigner, 1971, and he was a well-known figure. I didn't know exactly what he was doing. I had my first draft of this idea of an FCC lattice, and I let the elderly gentleman go ahead of me to use the photocopy machine, and discovered some years later that it was in fact his idea that I was working on. So I've been doing computer graphics of that, thinking that all you have to do is understand the geometry, and then it becomes easy. And I'm afraid that I've been selling this geometry for so long that it's somehow everyone knows it, and remain unimpressed by the symmetries that you can see in 3D, but they are the symmetries of quantum nucleodynamics, or the quantum physics at the nuclear level. So I think we have is a choice between amorphous nuclear models, which is gaseous or liquid, and lattice models. In terms of their quantum properties, they're identical. But what is of interest about the solid phase FCC lattice is that everything is computable. You know where the protons and neutrons are, and you can do interesting calculations from that basis. Tuesday evening, I hope to talk about this a little bit. I've been talking about these things for a few years. I just want to show you a couple of pictures of things we've done before the cold fusion years. There are problems in explaining the fission of uranium, for example, that also date back to the 1930s, that we can explain quite nicely if you include the geometry of the FCC lattice, different planes, and whether they're easy or not easy to cut. There's something similar with palladium fission, which Meitner was looking at in the 1990s. And more recently, there's the spontaneous fission of mercury-180, which both by the liquid drop model and the shell model is predicted to give symmetrical fission, and in fact it gives asymmetrical fission like uranium. And this is easily explained in terms of the lattice structure. The substructure is the key. And it's easy. This is geometry. It's a pain in the neck, and it must be computed. There's no easy way around that. But you can do interesting things with the FCC geometry. Now, I don't want to get into this more than necessary, but the one point I want to make here that I'm sure most of you remain unconvinced of is that the colors and the location of these nice tetrahedrons and octahedrons that are within the FCC are all isomorphic with the structure of the wave equation and the quantum numbers that are there. I think I will just flip through these. These are the kinds of things that you can do with a known geometry, and from there you can add hypotheses to predict states. For example, the proton plus lithium-7 excited state breaking into 2 alpha particles, for which you need some underlying geometry. So in conclusion, I think maybe that Meitner has done us a big favor in producing his quite uninteresting SCP packing theory of the nucleus, but somehow he has managed to get his work recognized. I think we have to go back, do comparisons of simple cubic packing versus Wigner's face-centered cubic packing, but that is the main choice between those two. Again, it's the Copenhagen interpretation that I think we can throw away and go ahead and do a deeper level of nuclear structure. Thank you very much.
Okay. I'm not going to tie everybody up because I want to get out and exercise and eat and drink or whatever. I want some critical information, and that is, where is the talk tomorrow and what time is it?
Where is the what?
Your lecture. Tomorrow.
Oh, upstairs, 322. There's a room upstairs.
I can't come to the meeting tomorrow, but I'd like to ask you if you can give us your computer code so we can verify your binding energy calculations and so on.
Yeah, my pleasure. The graphics is available also.
I'm not interested in the graphics.
Right, the C code.
I want to be able to calculate.
Yeah, C code for that and Excel spreadsheets. It's all available on the web. I'd be happy to get it to you. Yeah. Room 322, I think, is where. Yes, ma'am.
First of all, I'd like to say I truly agree with throwing away the Copenhagen interpretation. I think that's a great idea. Everybody should applaud to that. And then I think also the concept of structure inside of a nucleus is absolutely imperative if you're going to understand something like fission or fusion. I think that it's pretty much impossible to, or it's really imperative to have a structure. Otherwise, if you just have an amorphous gas or amorphous liquid, there is very little explanation for fusion or fission. So I want to applaud you on that one, too. I also wanted to comment that the quantum QCD lattice, they use quark masses that are hundreds of times bigger than what is realistic, and then they try and calculate moving those quark masses slowly down so they can interpolate, and that's how they get around the Heisenberg, which seems to me to be pretty much that they're cheating. So anyway, I just wanted to make those comments.
Yeah, thank you very much. The idea of getting to substructure, I think, is we are agreed on that.
I agree with you on the need to reinterpret the Heisenberg uncertainty relationship, but tomorrow I'll be giving the paper from Jean-Luc Palais on relativity and how it actually adds so you can use the Heisenberg uncertainty relationship in the nucleus and in approaching the nucleus. So it'll be interesting to see. I don't think it's the only way, but it at least does answer that question.
Yeah,
so
yeah,
it'll be interesting to see that.
I look forward to that.
Nuclear structure has a very variety, as you know. Sometimes the ground state, just like a shell model ground state, but sometimes it's a cluster model, or sometimes yours, or so it's just like a different of base. Which wave function first you choose is the most important to express the nuclear structure, seems to me.
This is in the textbooks. I don't believe it. I think this is
I'm learning the textbook for many years.
I think this is indication of an immature field if you have conflicting models and to say sometimes we apply this one, sometimes we apply that one.
Yeah, right. So sometimes this nuclear structure shows the kind of lattice structure. That's true, I guess.
Thank you.
Let's give quick